Question 1 gives us a histogram. We've got 50 plums. They vary in weight. This is effectively our X values of the weight of the plums. And notice that we don't have individual weights of each of the plums. Instead, they're put into groups, 1, 2, 3, 4 groups of 2 grams wide. Part A, we've been required to show an estimate for the mean weight of the plums. Now, if we had the weight of all the plums, we would add all the weights up, get a total weight of the whole lot, and divide by 50. But we haven't got that, so we're going to have to use, in group 1, for example, we're going to have to use the mean weight. All the plums that are in this group, we're going to say, are 61 grams. All of the plums in this group, group 2, 63, all of the plums in this group, 65, and all of the plums in this group, 67. So how many are there in each of these groups? Well, we're going to have to work backwards, really, from frequency density. And frequency density is defined as the frequency, in other words, the number of occurrences, divided by the width of the class. And this is what we've got plotted down here. So to get back to frequency, we've got to multiply the frequency density value by the class width for each of these columns. So for column 1, the frequency is equal to the frequency density value, which is 3, multiplied by the class width, which is 2, which is equal to 6. So there are 6 plums in group 1. And if you work out the other frequencies, 24 are in this group, 16 are in this group, and 4 are in this group. And these will add up to our total of 50 plums. So the mean weight of all of our plums is the weight of all of the plums divided by the number of plums. It's the average weight. But because we can't get at individual plum weights, we've got to treat each column separately by taking the number in each column, multiplying it by the midpoint weight, summing them all up, and then dividing by the total, which is the sum of all the column frequencies, which we know to be 50. So this is equal to 6 times 61 plus 24 times 63, and so on. And if you put that into a calculator, you get 63.72 grams, which is the answer they wanted. Part B wants an estimate for the standard deviation of the 50 plums. Happily, the formula for standard deviation of a distribution such as this is in the formula sheet, and here it is. What's underneath the bracket here is MOSM. The mean of the squares take away the square of the mean. Now we've got the mean already. This is 63.72 grams. So all we've got to do is square it and take away from the sum of the squares. Now again, we haven't got individual plum weights. So we're going to have to say, for column 1, for example, this is going to be 61 squared multiplied by 6. We're taking the weight and squaring it and saying, well, we have 6 values of that 61 squared. Again, 63 squared multiplied by the 24, 65 squared multiplied by the 16, 67 squared multiplied by the 4. So our sum becomes this. And if you pop that into a calculator, you get the answer of 1.587. And on it goes. And that's the answer to part B. So looking at part C, it now says that the scales were wrong and each plum now weighs 5 grams less than originally thought. What effect does this have on the standard deviation? Well, the standard deviation is a measure of spread of the results. And that 5 gram discrepancy will just push the whole of this distribution 5 grams leftwards. So this becomes 55, and this will become 63. But the standard deviation, in other words, the variation of weight of the plums, will remain the same. And that is the verbal answer to part C.